Raman High School, the pioneer of IIT Foundation in Tri-Cities.
Hello children, this is Karunakar Reddy, mathematics teacher, Raman High School. Today I would like to discuss about real numbers from 10th class mathematics. Real number chapter is not only important for SSC point of view, this is also useful in various Olympiad examinations like RMO, Pre-RMO, AMD. This real number chapter is not a new chapter for you at all because already have learned this chapter in 9th standard itself. In 10th standard, we are going to learn real numbers once again. We are going to revise it. Mainly in real number chapter, we are going to cover the introduction of real numbers, Euclid's division algorithm, fundamental theorem of arithmetic, rational numbers and their decimal expansions, irrational numbers and their properties, and some calculations on irrational numbers. And a new topic is introduced in real numbers, that is logarithms. So in these logarithms we learn some calculations and some properties of logarithms which are needed in our day-to-day life. So in real number chapter, in 10th class annual examination we can expect 7 to 8 marks. So this is one of the important chapter in point of view of SSC examination. And before getting into real numbers originally, let us see what we have learnt in previous classes. Here, natural numbers, whole numbers, integers, rational numbers and irrational numbers. These all number systems you have learnt in your lower standards, in your previous classes. Your natural numbers are also called as counting numbers. They are 1, 2, 3 and they are denoted by n. Whole numbers are denoted by W and the whole numbers are 0, 1, 2 and so on. Your whole numbers are obtained by adding 0 to this natural number. That is nothing but natural numbers along with 0 is called as whole numbers. Your integers. Integers are denoted by Z, they are Z numbers, and integers are whole numbers along with the negatives of natural numbers. Negatives of natural numbers nothing but -1, -2, -3 and so on. So integers are 0, -1, -2 and so on. Here 1, 2, 3 and so on. Next, rational numbers. Here rational numbers are denoted by Q. The numbers which are of the form P by Q, where this P comma Q are integers and Q is not equals to 0. These are rational numbers. And irrational numbers. Irrational numbers are the numbers which cannot be written in the form of P by Q and they are denoted by Q dash. So there are some other definitions for irrational numbers. The definitions we learn in irrational numbers. While I am dealing with irrational numbers, I will tell you some other definitions of irrational numbers. So now you remember just what is the definition of irrational numbers as the numbers which cannot be written in the form of P by Q, where Q is not equals to 0. And about these natural numbers, whole numbers, integers, rational numbers and irrational numbers, you have already learnt in 9th standard. This chapter already you have in the 9th standard itself. And so after learning rational numbers and irrational numbers, so we can extend these numbers to some other numbers by combining some two number systems. Here rational numbers and irrational numbers are there. Their combination is called as real numbers. Here rational numbers combined with irrational numbers. This one you will read as Q union Q dash. Q union Q dash nothing but rational numbers along with irrational numbers. Rational numbers combined with irrational numbers. That is called as real numbers. This is what we are going to discuss now. So let us see some divisions here. What you have learnt in your 3rd and 4th standard. See here, 35 is divided with 2. We are getting the remainder as 1 and quotient as 17. Here, 35 is divided with 3. The quotient is 11 and remainder is 2. And in all the cases, 35 is divided with some number. And in all the cases, you got some remainders here. 1, 2, 3. Here 0, 0 you got. In all these cases, we can observe that the remainder is always less than this divisor. You know this? This is a divisor, this is a dividend, this is a quotient, this is a remainder. In all these divisions, here I have given 5 divisions. In these all, the remainder is always less than this divisor. And in some divisions, you can see that the remainder is equals to 0. The remainder is equals to 0, nothing but this 35 is exactly divisible by 5. So here I want to conclude that while we are taking divisions, the remainder in a division is always less than the divisor. And let us take some other normal division here. Here dividend is A, divisor is B, quotient is Q and remainder is R. By using Euclid's division lemma, this is already you know as division rule or division fact. That is, dividend equals to divisor into quotient plus remainder. That is written as A equals to BQ plus R. Here dividend equals to divisor into quotient plus remainder. In this all, we have observed that the remainder you are getting either 0 or more than 0. And one more thing we have observed that all the remainders what we are getting are always less than this divisor. If you observe in this division, this is a remainder. This remainder can be equal to 0 because we have observed here remainder can be equal to 0 and this remainder value must be less than this divisor. Therefore, we can write a condition on this remainder. The condition is 0 less than or equals to R less than B. This is the best condition you have to observe in your lower standards. The condition is 0 less than or equals to R less than B. This is an important condition in respect of objective examination. From these all divisions and this condition, we can develop a lemma, that is Euclid's division lemma. This Euclid's division lemma is first observed in 7th book of Euclid's Elements. About Euclid's Elements you have learnt in 9th standard as elements of geometry. In that elements of geometry you have learned that there are 13 elements in Euclid Elements. In that 13 elements, in the 13 books, in 7th book you will find Euclid's division lemma. About Euclid division lemma we are going to discuss now. Now let us see an example to find out the HCF of 160. Here to find out the HCF of 160, already you have a method in your 6th class, so that is long division method. By using this, you can find out the HCF, and here the HCF is 20. Here we are considering 20 as HCF when you are getting the remainder as 0. This is a method already you know. Okay, now let us see how to find out the HCF of two numbers by using Euclid's division lemma. Let us take 160. Here 100 is divided with 60 and you are getting this division. Let us take this division and let us apply division rule for this. By using division rule, you can write 100 equals to 60 into 1 plus 40. Here 60 into 1 plus 40. Divisor into quotient plus remainder. Now let us take these two numbers. For these two numbers we have a division here. By using division rule, again you can write 60 equals to 40 into 1 plus 20. Here 40 into 1 plus 20. Now again let us take these two numbers. This process we are going to continue up to the remainder we are going to get as 0. Here the remainder is not 0, therefore we are continuing this process. Here the remainder is not equals to 0, therefore we are going to continue this. Now let us take this 40 and 20. Therefore 40 and 20 again we have a division. Let us take this division. That is 40 equals to 20 into 2 plus 0. Here the remainder is 0. If you are observing the remainder as 0, the divisor what you are getting here, that is called as HCF. Therefore, the HCF of 100 comma 60 is equals to 20. So this process of calculating HCF is called as finding HCF by using Euclid's division lemma. If you know how to calculate the HCF of two numbers by using division method, finding the HCF of two numbers by using Euclid's division lemma is very easy. In page number 4, you have a think and discuss. Actually, this you have to think and discuss with your friends. But so this is the first chapter what I am explaining now. That's what I want to say, how to think and discuss this type of problems. Here the problem is, can you find the HCF of 1.2 and 0.12? Here in this 1.2 and 0.12, the smaller number is 0.12 and greater number is 1.2. Every time you will divide big number with small number. So on this division, what you are getting the remainder you can write as 1.2 equals to 0.12 into 10 plus 0. Here you got remainder 0. If you are getting remainder 0, directly you can take this divisor as a HCF. Therefore, the HCF of 1.2 comma 0.12 equals to 0.12. This is one method. And there is some other method to calculate the HCF of 1.2 and 0.12. So which are decimals. So method 2. First convert this 1.2 into a rational number, otherwise into a fraction, that is 12 by 10, and 0.12 can be written as 12 by 100. To find out the HCF of these two numbers, find out the HCF of numerators divided by the LCM of denominators. So that is nothing but here HCF of 1.2 comma 0.12 equals to HCF of 12 comma 12. Here these two are the numerators here. That is LCM of 10 comma 100. Here 10 comma 100 are the denominators. And it is very clear that for 12 and 12 HCF is 12. And the LCM of 10 comma 100, you know how to find out the LCM of 10 and 100. You have learned in lower standards. The LCM of 10 and 100 is 100. So, here you got 12 by 100. If you convert this into decimal, you are going to get as 0.12. Here you are getting this one as 0.12. What you are getting now? HCF of 1.2 comma 0.12 is 0.12. Here this is by using Euclid's division lemma. Here you are getting HCF as 0.12. In method 2, also you are getting 0.12. Therefore you can conclude the HCF of 1.2 comma 0.12 as 0.12. Now let us see some applications of Euclid's division lemma. Here you have an application, that is, show that every positive even integer is of the form 2q and every odd positive integer is of the form 2q plus 1, where this q is some integer. Now let us see the proof of this. Let us see how you will prove this. Now let us take a positive integer a. Here we are taking a positive integer a. By Euclid's division lemma, we can write a equals to bq plus r, where 0 less than or equals to r less than b. Here this is Euclid's division lemma, already we have explained. Here a equals to bq plus r, where we have a condition on r, that is 0 less than or equals to r less than b. Here in question you have even number must be in the form of 2q and odd number must be in the form of 2q plus 1. Here you have 2 and here also you have 2. Then let us take the value of b as 2. Take b equals to 2, then a equals to 2q plus r, 0 less than or equals to r less than 2. Now here you can observe that this remainder is 0 or more than 0 and less than 2. Therefore the possible values of r are 0 comma 1. There is only two possibilities for 0 comma 1. In these two cases we will check for this positive integer whether it is going to become a even number or odd number. Let us go with first case 1. Take r equals to 0 in a equals to 2q plus r, that is a equals to 2q plus 0, then a equals to 2q. Here what you are getting, a equals to 2q you are getting, and already you have the definition of even number, that is the number which is exactly divisible by 2 is called as even number. Here a is 2 into q. Here this is in the form of 2 into q, therefore that is exactly divisible by 2, therefore 2q is a even number. Therefore this positive number is a even number. Therefore a is in the form of 2q. Therefore we can conclude that an even number will be in the form of 2q. Therefore a even number will be in the form of 2q. Let us go with second case 2. Take r equals to 1, a equals to bq plus r. We are taking r equals to 1 in this, then what you are going to get? A equals to 2q plus 1. Here already we have proved that 2q has an even number. Here we have proved that 2q has an even number. Even number plus 1, that is a odd number. By the definition of odd number, even number plus 1 will be odd number. Therefore here even plus 1 is odd number. Therefore 2q plus 1 is a odd number. Therefore a is in the form of 2q plus 1. Therefore, a odd number will be in the form of 2q plus 1. In first case, we have proved that even number will be in the form of 2q, and in the second case, we have proved an odd number will be in the form of 2q plus 1. From these two cases, we can conclude that every positive integer will be either in the form of 2q or 2q plus 1. In that positive integers, even numbers will be in the form of 2q and the odd numbers will be in the form of 2q plus 1. So this is a proof of every positive even number will be in the form of 2q and every odd positive integer will be in the form of 2q plus 1. Now let us see some problems in exercise. Now let us see some problems in exercise. Here we have a problem, third problem in exercise 1, that is use Euclid's division lemma to show that the square of any positive integer is of the form 3p, 3p plus 1, 3p plus 2. Now let us take a positive integer a. Here we are taking a to be a positive integer by Euclid's division lemma. We have a equals to bq plus r, where 0 less than or equals to r less than b. This is what Euclid's division lemma is. In this question we can observe that here we have 3p, 3p plus 1, 3p plus 2. Just note down this 3. Then you can observe that we are going to take b value as 3. Here we have b value. This b value we are going to take as p. 3. That is a equals to 3q plus r. Here 0 less than or equals to r less than 3. From this we can observe the values of r as r equals to 0, 1, 2. These are the only 3 cases. These are the only 3 possible values for r you will get. So we have 3 cases here. In these 3 cases we are going to check whether the square of a positive integer will be of the form 3p, 3p plus 1 or 3p plus 2. Now let us take first case, case 1. In case 1 we are going to take r equals to 0. Take r equals to 0. We are going to substitute r equal to 0 in this. Then that is a equals to 3q plus 0. Therefore a equals to 3q. Here a equals to 3q you got. Here a is a positive integer. But what do you want here? You want the square of a positive integer. That's what we'll take squaring on both sides. The squaring on both sides will give you a square equals to 3q whole square. That is a square equals to 9q square. Here a square equals to this 9q square can be written as 3 into 3q square. So this 3q square we are going to take as some p. Therefore a square equals to 3p, where p equals to 3q square. This 3q square we are taking as some p. Therefore we can conclude that the square of a positive integer is in the form of 3p. Let us take case 2. In this case 2, take r equals to 1. In previous case we have taken r equals to 0. Now r equals to 1 we are taking. This r equals to 1 we are taking in a is equals to 3q plus r. That is a equals to 3q plus 1. Here r equals to 1 it is substituted. Here a is a positive integer but we need the square of a positive integer. That's what we will take squaring on both sides. That is a square equals to 3q plus 1 whole square. Here a square equals to, here we can use a plus b whole square. By using a plus b whole square, we can write as 9q square plus 6q plus 1. Then a square equals to 3 into 3q square plus 2q plus 1. Now let us take this value as some p, some integer p, that is a square equals to 3 into p plus 1, where p equals to 3q plus 2q. This 3q square plus 2q is considered as p, therefore you are getting 3p plus 1. Here we can observe that the square of a positive integer is in the form of 3p plus 1. In previous case we have proved that the square of a positive integer is 3p. Now we have proved as the square of a positive integer as a 3p plus 1. Let us see the next case. So in case 3, let us take r equals to 2. In previous cases we have taken r equal to 0 and r equals to 1. Now r equals to 2. This r equals to 2 you will take in a equals to 3q plus r. 3q plus r. In this we are going to substitute r equals to 2. Then that is a equals to 3q plus 2. Here we have a positive integer as 3q plus 2, but we need the square of a positive integer. That's what we will take again, squaring on both sides. Squaring on both sides. A square equals to 3q plus 2. Here again we have a plus b whole square formula. By using that, a square equals to 9q square plus 12q plus 4. This can be written like this. A square, that is 9q square, 12q plus 3 plus 1. Here we are writing 4 as 3 plus 1 because we have to write these 3 terms as the product of 3 and something. That's what we are writing 4 as 3 plus 1. From this 3 numbers we can take 3 as a common factor. That is a square equals to 3 into 3q square plus 4q plus 1 plus 1. Here 3 into something. Here 3 into something we have. This bracket value we are going to take as some p. Therefore a square equals to 3 into p plus 1, where p equals to 3q plus 4q plus 1, 3q square plus 4q plus 1. We are taking as some p, therefore a square equals to 3p plus 1. So here we can say that the square of a positive integer is of the form 3p plus 1. So in first case what we got? The square of a positive integer is in the form of 3p. In second case you are getting a square as 3p plus 1 and a square equals to 3p plus 1. But if you see the question, I think you have your textbooks with you. If you see in that, suppose in new textbooks you may not find this mistake, but here what I have written in the question, you can observe that there is a 3p plus 1 and 3p plus 2. But according to this, you can conclude that the square of any positive integer will be in the form of either 3p or 3p plus 1. There is no 3p plus 2 in the question. Just strike out that 3p plus 2 in the question. The question is, use Euclid's division lemma to show that the square of any positive integer is of the form 3p or 3p plus 1. So there is a 3p plus 2 in the question, that must be striked out. That is not there in the question. So in a newer version of textbooks, you can find that only 3p and 3p plus 1. There is no 3p plus 2 in that. So we can conclude that the square of any positive integer is of the form 3p or 3p plus 1. Now let us see fifth problem in exercise 1. That is, show that one and only one among n plus 2 and n plus 4 is divisible by 3, where n is a positive integer. The meaning of the question is, among these three numbers, only one number is divisible by 3. That is what we have to prove. By Euclid's division lemma, we have that every positive integer will be of the form 3p or 3p plus 1 or 3p plus 2. By using this concept, we are going to prove that only one among these three numbers is divisible by 3. So, by using Euclid's division lemma, every positive integer will be in the form of either 3p or 3p plus 1 or 3p plus 2. Now let us take the positive integer as 3p. So in our problem, n is a positive integer. I am taking that positive integer as 3p now. Take n equals to 3p. So in these three numbers, the first number is n is 3p. Second number is n plus 2, that is 3p plus 2, and the third number is n plus 4, that is 3p plus 4. Here n is 3p, n plus 2 is 3p plus 2, n plus 4 is 3p plus 4, because we are substituting n equal to 3p in these three numbers. In these three numbers, if you observe, here 3p is divisible by 3 because 3p is the product of 3 and p, therefore it is divisible by 3. And here you can observe this is a multiple of 3, but this is not a multiple of 3, therefore 3p plus 2 is not divisible by 3. And if you see this, 3p is a multiple of 3, but 4 is not a multiple of 3, therefore 3p plus 4 is not divisible by 3. So we can observe that among this n plus 2 and n plus 4, only 3p is divisible by 3, that is n is divisible by 3. When you are taking n equals to 3p, only n is divisible by 3. So let us go for the next case. Let us take n equals to 3p plus 1. Now again let us take these three numbers and check whether they are going to be divisible by 3 or not. The first number is n, and n value you are taking 3p plus 1. Second number is n plus 2. 3p plus 1 plus 2, that is 3p plus 3. You can take 3 as a common factor, it is p plus 1. 3 into p plus 1. Let us take third number. Here is a third number, n plus 4. Here n plus 4, here in the place of n, again you are going to substitute 3p plus 1. 3p plus 1 plus 4, that is 3p plus 5. If you observe these three numbers, here 3p is a multiple of 3, but 1 is not a multiple of 3. Therefore 3p plus 1 is not divisible by 3. Here let us see n plus 2. It is 3 into p plus 1. So this is the product of 3 and p plus 1. Therefore this is divisible by 3. Therefore n plus 2 is divisible by 3. Now let us see n plus 4 value. That is 3p plus 5. Here 3p is a multiple of 3, but 5 is not a multiple of 3. Therefore 3p plus 5 is not divisible by 3. So we can observe that among these three numbers, only n plus 2 is divisible by 3 because this is 3 into some p plus 1. So among n plus 2, n plus 4, only n plus 2 is divisible by 3. Let us go for the next case. Take n equals to 3p plus 2 and again take the first number. The first number is n, that is 3p plus 2, and second number is n plus 2, 3p plus 2 plus 2. It is 3p plus 4, 3p plus 4 and n plus 4, 3p plus 2 plus 4, 3p plus 6, that is 3 into p plus 2. And let us observe these three numbers now. Here the first number is n. In this 3p is a multiple of 3, but 2 is not a multiple of 3, therefore this is not divisible by 3. In the same way, if you see n plus 2 value, here 3p is a multiple of 3, but 4 is not a multiple of 3. Therefore, 3p plus 4 is not divisible by 3. Therefore, n plus 2 value is not divisible by 3. Again, n plus 4 value, it is 3 into p plus 2. 3 into p plus 2, then you can say that it is a multiple of 3. Therefore, it is divisible by 3. Therefore, n plus 4 is divisible by 3. So, among these three numbers, only one number is divisible by 3, that is n plus 4. So if you observe these three cases carefully, in all the three cases, we observe that among n plus 2, n plus 4, only one number is divisible by 3 if n is a positive integer.